maximum and minimum problems. Probably one of the key uses for mathematics is optimization problems. You know, where find maximum profit or minimum costs or whatever, those sorts of things. So if we can reduce things down to an equation, then find the maximum and minimum of those equations. Now, we already looked at that this year with quadratics. When we could reduce it down to a quadratic, we said, okay, well, all we really need to do is find the vertex of that quadratic. So we didn't actually need to draw the graph, we just had to locate the vertex. Well, now that we've got calculus, we don't have to be restricted to quadratics, because we can find minimum and maximum turning points of any graph using our calculus. So basically we're going to have a word problem, and in that word problem it's going to be asking us to maximize or minimize some quantity. So the things we do, we need to reduce the problem down to a set of equations. So we're getting this word problem and we're taking it out of words and putting it into mathematics. Usually there'll be two equations, sometimes more, sometimes there might only be one, but most of the time we'll bring it down to two equations. Now, one of those equations, it'll be obvious because it'll be what we're trying to maximize or minimize. We're going to need an equation for that. The other equation is usually some piece of given information in the problem. So they might tell you the amount of material you're going to use or something like that. So then we rewrite one equation, so the one that we're trying to maximize or minimize, with only one variable. And so that's by using the other equation, making one the subject, a bit like parametrics. Make one the subject, substitute it into the other one. And then we go and use calculus to find our maximum or minimum. All right. So we've got a rope, 36 metres long. So there's our piece of given information. We're going to cut it into two pieces, as you do. The first one we're going to bend to form a square. And the other one's going to be a rectangle, but one side of the rectangle is going to be the same length as the square. We need to find the length of the square so we maximise the two areas. So why would we want to do something like this? Well, maybe we're trying to trap some creature in a little pen or something. Well, 36 metres, I suppose that's a reasonable length, isn't it? But here's a problem to solve. Well, I like to draw pictures to try and visualise the problem. So we're going to get our piece of rope, we're going to cut it, we're going to form two shapes. One's a square, one's a rectangle. Let's give it some dimensions, some pronumerals, so we can turn this into an equation. Creatively, I used S for the side of the square. Don't know how I thought of that, but there you go. Now my rectangle, one side's going to be S because they said it was the same as the square, and I called the other R for rectangle. Yeah, sure. So my first equation, what it is I'm trying to maximise or minimise, in this case they've told me to maximise the area. So the area of the two shapes, first one would be S squared, the second one would be RS. So I've got my area, but it's in terms of two variables. And when we're doing our calculus, we like to have it in terms of one. That's why we need the other piece of given information, that the length of our rope is 36 metres. So, in other words, the perimeter of these two shapes would be 36. So 6x plus 2r is 36. So it's now a matter of making either r or s the subject of this second one, substitute it into the first one. We don't want to make life hard for ourselves, so the logical one to make the subject would be r, because I've only got to substitute it into... Well, you could make s the subject if you wanted to, but you've only got one spot to substitute r in. So I'm going to make r the subject. R is 18 minus 3s. Substitute it into a, and we end up with our area formula. Now, in this case, it did turn out to be a quadratic. So we actually have a choice here. I could use my quadratic theory and just find the vertex. But for the sake of our example, because we're talking about calculus, let's do it that way. So there's my formula. Let's differentiate it. I'm going to need the first derivative to find the stationary point. I'll also need the second derivative so I can prove it is a maximum or a minimum. Stationary points occur, in this case not dy dx but dA ds equals 0. Solving that, I've got s is 9 on 2. And when s is 9 on 2, the second derivative is negative 4. Well, in this case, it's negative 4 for everything because we've got a parabola, so it just has a constant concavity. But that's less than 0. That's the key thing. So I know that that's a maximum turning point. So I answer the question. It's not actually asking for the area. It just wants to know the side length when the area is a maximum. So I know the side length of the square is 4.5. That area will be maximised. If you look at that carefully, you'll notice if I was to sub back in and find the length of the rectangle, yeah, it also turns out to be a square. And it's back to this idea with a lot of these shapes, the regular shape will maximise a problem for you. All right, we're going to have our buckets. An open cylindrical bucket, we're going to hold the largest volume of liquid in our bucket. We know the total surface area of the bucket conveniently works out to be exactly 12 pi. That was lucky. We're going to find the height, the radius, and the volume of our bucket. So there's my bucket. It's got a height, it's got a radius. We're trying to maximise volume. Volume of a cylinder is, of course, pi r squared h. And the other piece of information, I know the surface area of my bucket. Be careful here. Notice it's 1 pi r squared. Yeah, because if you had 2 pi r squared, it'd be a pretty useless bucket. You pour the water in and it just goes everywhere. Oh, but lucky for us, look, pi will cancel. Gosh, I was lucky that was 12 pi, I tell you. We're going to make h the subject. That's going to be the easiest one to work with. So h is 12 minus r squared on 2r. Subbing that back into my volume. And I end up this time with a cubic. Okay. So this is where the calculus certainly comes in handy, because with the cubic, I can find the maximum and minimum points. In this case, we want to maximise the volume. So we want to find that maximum point. Okay, there's volume. Differentiate it. There's dVdr. Differentiate it again, our second derivative. Stationary points, in this case, dVdr is equal to 0. We get r is plus or minus 2. One of those will be the maximum, one of those will be the minimum, because we know it's a cubic. I want to test for the maximum. Which is the logical one to pick? Yeah, plus 2. Because I'm pretty sure, I'm fairly confident the radius of my bucket is not going to be negative 2. Okay, so positive 2 would be the logical choice to test here to save time. So sub in 2, yes indeed, we get a negative number, it's minus 6 pi, so when the radius is 2. But that doesn't answer the question, because in this case they did ask for more information. They wanted the radius, the height. Well, subbing in, the height turns out to be 2 again, so once again we've got that sort of symmetry in the shape. And the volume turns out to be 8 pi. So 8 pi units cubed, and that's when radius and height are both 2 units. Okay, let's play with some maxima and minima questions.